Okay. So now, let's see. Then the other one is what? Pareto QQ. Okay. We can even find log normal. There are so many of them in the log normal QQ. You know the log normal distribution. Okay. So it's related to also the normal distribution. I'll show you that the Pareto is actually log of all the exponential. Okay. So now let's see. We want to now check. Did I ask you to install the insurance data package? You've done that one. Okay, good. So let's look at the insurance data package too. Why are we doing all this? So that in exam, if I give you some of these things, it becomes easier for you. Okay. So there's auto BI, there's auto claims. So let's look at the claims. The claims data is what? Claims experience from a large Midwestern U.S. property and casualty insurer for private automobile insurance. Okay. So there's amount paid. So we want to see, let's first get a histogram of the amount paid. I think, So you need to do insurance, library insurance, and then the data set we want to use. In this case, you have to call the data. So it's auto claims. So you need to do this, then it becomes available. That's how the insurance data works. So we now have what? The auto claims in our environment. Okay. We are interested in the amount paid, right? So let's look at a histogram of it to see how it looks like. So it means I need to call auto claims, and then I put the dollars. And remember, for a data frame, because when we came here, it says what? It is a data frame format. It's what? The format of this is what? A data frame with us 6,773 observations. So this is a real data set. It has references. So for example, if let's say in your level 400 project, you want a data set to work with, these are some of the data sets you can. And it's large enough to do whatever you want to do. Okay. So let's look at a histogram of it to see how it looks like. Well, so we do a histogram. It's like this. I need to take out the main. Okay. And then I want to fill the entire space. So I give it a margin of 4411. And then I redo this. There it is. And then the air slab is not good. Come on, connect this. The air slab is not, as I said, as soon as I see this, I know you don't come to class. So what do we do in order to change it? Wait. Who has not talked in this class? Hey, you. Yes. What should I do in order to change? Yes, you. What should I do in order to change that one? You've not spoken before, have you? You, yes. Good. Okay. So now you've spoken. S-Lab and what again? Maybe the amount paid. Okay, good. Okay, so let's say amount paid. Okay, good. So please, so this is fine. Okay. Then your friend. What can you say about the distribution of the amount paid, the claims amount paid? It is That's what you tell the manager. Yes, it's skewed to the right, but how would you interpret it to the manager? Okay, all right. That's good. Yes. What else can you say about this? The amount received were less than the average. What does that mean? Don't complicate things. I want you to speak in a language that any layman will understand. So if you say the amount were less than the average, then what else? You know, in statistics, you look at the peculiar things. Okay, so what can you see here that is so distinct? You talk about it, and then if you can talk about the central, that's why you do measures of central location, measures of variation, skewness. So you started with the skewness, even the kurtosis and so forth. So what else? What else can you say? Yes. The large amount, what can you say about it? So if you are working at that company, those large amounts, the frequency with which they occur, you will say it is what? Good. Or less. So it's rare. Is that okay? So that's very important, because in decision making, you tell the manager that, well, most of the claims are what? Very low. If you are at an insurance company, you don't really care about this, right? But if any of these ones occur, it may lead to what? It may lead to bankruptcy. Okay, so if you are there, one of the things you do is that you do what we call reinsurance, isn't it? Now, if you want to do reinsurance, where will you cut off? That's a decision you need to make. And that decision will depend on what? The probability of what? Exceeding that amount. Because the reinsurance company will only come in when what? That amount, the retention level is what? Is exceeded. And so forth. So these are practical things but you should be able to interpret a graph, not to your understanding here as skewness, kurtosis, and so forth. Whatever you say with that, you must interpret it in a language that the secretary to your board of director or whatever will understand and say it in a meeting. Is everybody okay with this? So those are some of the things you will be doing when you start working. So please don't write and say the skewness, it is positively skewed. They won't understand what you mean. Is that okay? So you can talk about your statistics, but every time interpret it in a language that everybody will understand. Now, larger claims come, but they come less frequently. So maybe in 2 years, you are not even experiencing any of the large claims. But suddenly there is rain and cars are being swept aside, or there's a fire outbreaks up, and then you have some of those. Okay, good. So now, even though we are here to do estimation, true likelihood and moment, we can now, because of what we've learned about quantals, okay, or we can only fit this one if we do those estimations, so that we can estimate lambda, and then we can use that to fit what? A probability distribution. And this is what I wrote over there. We cannot be fitting a distribution to this. Why is it so? Can we fit a probability distribution to this one now? Why? Because what? Yes, because the frequency is not a relative frequency. How do we convert it to a relative frequency? What do we do? One person. What should I do? What can we do in order to get it in a relative frequency? Is that what you will do? We can do it straight away in histogram, right? It's what? Yes. So the function freg. So you are not wrong. Yeah. So if you don't know how to use, you can go through your usual understanding of what? Relative frequency, which is that you will divide each of the frequency by what? But it means you have to go and create a table. You did not create any table. You just passed on the values to histogram. But if you want a relative one and you want to go through then you have to table them, convert your discrete data into now categorical so that you have, the groups, and then you can now find so freg equal to what? By default it is what? False. So this should be what? True. Are you sure? Okay, we can try. We will see whether it is that or not. So frequency is true by default. So it has to be false, and then we'll get it in relative frequency term. So this is okay now for us to fit a distribution. It's the same graph, nothing changes, except what? This place is now frequency, but it's what? Density. So this is where you can now fit your. But if you do this and you fit or you see maybe red line at the bottom, because you are talking about between 0 and 1, that's against 5,000 observations. Okay, so that's what I was explaining over there. Practically, that's it. Okay, so now let's see how are we going to check this with exponential distribution, right? So let's see, ESP, QQ, right? They say X data is equal to, and the data is this one. So we put it here, there. So you see quantile from a standard exponential, and then the other one is X. X is the order statistics. Is that okay? So this is what we mean by what? Exponential QQ plot or quantile plot. What can you say about the fit of exponential distribution to this data? To the claim data? Remember the rule. If it fits it well, we should have what? A straight line. Do we have a straight line here? Yeah, it's more or less like a curve. What else can you say about them? What else can you say? What is peculiar about? That's what you do. You look, yes. There are, of course, there will be positive correlation. There will be. But what peculiar thing can you see from this graph? There are outliers. Why do you say they are outliers? Good. So you say that there are some two particular values that are very distinct from the rest. Okay? Is that okay? And that's what you see over here. So if you look at it, they are over 60,000, almost close to 60,000, right? As against those that are what? Majority of them were below what? 2,000. And that's what you see from your histogram. Okay, so those two observations, they are somewhere here, but you can't see them. Do you see? Because the value is what? Maybe 1, as opposed to 1,000, almost, what was it? 5,000, right? 5,000. So if you are comparing 5,000 and there's 1 here, you won't see anything with your naked eye. So that's what we are seeing in the graph. Is everybody okay with this? Okay, all right. Now remember that we said that we can also, this ESPQQ, I can, if you remember, I can now, I said the log of it is what? Is Pareto. Okay. So I can use a Pareto QQ. I'll come back to this, but let's use a Pareto QQ. Then we look at how this will look. We can compare. When I finish, I'll do all of them together. So this is a Pareto. This and the exponential, which one fits the data well? Which one? What can you say? Which one? So if you look at it, well, this one, it fits most of the lower part, or the, what do we call it? The lower claims or the lesser claims that you find in your histogram. Here, most of them are within this group. It fits as well. So if you look at it. But remember, I said in an insurance company, you are not really interested in those smaller claims, because they come so many, but they are not, unless they come so quickly that it may lead to bankruptcy. But the larger ones, once one comes and you're unable to pay, by the time you realize you're at Joy FM, and then it goes to City, by the time you get to Peace FM, the insurance company is gone. Do you get what I'm saying? So that's what you are particular about as an insurance company. So those who do betting, right? If you bet, you know, there's a favorite, I've forgotten, there's a statistician who said that if I want to bet, then I'll build a casino. They will always win, right? Occasionally somebody will win big, right? Okay. But do you know what they do? You insure against those winnings. So yes, one person, then and everybody will go and bet. But when that happens, there's an insurance company that is taking that kind of winning to pay. Other than that, you'll be out of business. Because there's also the likelihood that one day, so many people will win, and then you are bankrupt. So those are some of the things we use in risk management. Okay. So what do we do? Now, we look at Pareto. So if you look at the Pareto, that one models the tails better than the exponential. Is everybody okay with this? So if I'm drawing a straight line here, I'm likely to touch one of the outliers. It is now on the same line with most of them. So that such a distribution will be better. Okay. I can go on and try the log normal. So when you go home, please check the others. There are other QQ plots within this reinsurance. So it's a very good package. Later on, especially for those who will be working in, let's say, claims department and so forth. That's a good resource for you. This log normal. What can you say? This is far better. It is actually modeling the both tails well, except that they are a bit distinct. So it is also telling you that there are some two very unusually low observations. We can't find them in the exponential and the Pareto, but they are quite distinct from the others. Is that okay? Okay, so later on, those of you who do masters and so forth, you will see robust statistics. Robust statistics are used to reduce the influence of outliers. Okay, and that's a huge research area in statistics. Okay, all right. So I can put all these together also by dividing this graph into 3 parts, right? To do so, I use what we call either MF row or MF column. So please, this function par, I think that's somebody's thesis, a PhD thesis. When you get time, you have more time. I don't have time like you do. Okay, go through it and learn how to use it. That's also a very good resource, the par. So you can use it to manipulate all the graph, the environment, what you see in there. But after this, you should move on to ggplot and so forth. We're talking about grammar of graphics. So R is, it's a massive resource that, you never finish learning some of them. Okay. My professor used to say that anything you cannot use how to do, it means it is your limitation, not the program's limitation. Because you can adapt it to any situation that you want, if you know the know-how. And there are so many. And in programming, you don't reinvent the wheel. People have done things, so all you need to do is to be able to build upon it. How can you build upon it? These are some of the things we are doing. And so the functions is very key. And it's not only here. If you do this and you use Python, the principles are the same. If you go to MATLAB, the principles are the same. So when you learn one, learn it well. The others, you get working knowledge with it, so that when you find yourself in any environment that they are using it, the learning curve shouldn't be steep. You go to work, within a week or two, you are at par with whoever is there. Okay. So I'll use the MF row. So I want, how many rows will come first? I say I want one row, but I need 3 columns. So I'll do it like this. See, if it was MF call, then it means the columns will come first. So if I do 1 and 3, the column will be 1, and then I'll do it row-wise. But that will not be nice. This one will be better. So I'll do this, right? So you won't see it, but it has partitioned the graph into 3 parts. So I'll now come back and rerun all the graphs that I did. So this is the first one. You see the exponential. I do the next one, that appears. I do the next one, that appears. So if I were to now present this, I pop this out. Okay, it becomes bigger. And there, you can now, if you are doing a presentation. Is everybody okay with this? Okay, so we've seen exponential. This is how it looks like. It doesn't fit the tails well, especially what? The unusually large observations. Then we move on to Pareto. That somehow fits them well. The upper order statistics a bit well, just that they are not like that of the exponential. It's better than the exponential. But then we talked about log normal, which is even far better. Okay. The next thing we will be doing later on when we do estimation is to now to be able to estimate those parameters of the log normal, of the Pareto, and then we will be checking how well they fit the tails and so forth. Any question so far? Okay. So this is what I did. I just rerun this. I think I need to make comments. Divide plot area into what? Into 3 columns. Into 3 columns. Then what you need to do is to rerun the entire graph again. It won't take into effect. In other words, if you do this, it won't automatically go and change it. You need to change it. Yeah. Okay. Any question? Okay, let me try and do this, then we can close. Okay, let's do this quickly and then we can close. Remember that I said the Pareto and the exponential are related. So if I have x, and x is exponential with parameter lambda, then if I have log, these are your 221 and 224, right? Transformations. Right. So if I find log s, then the log s will be a Pareto lambda. It may have a scale, sometimes it may be 2 beta, and it can even have a so this will be the shape. You can get a scale, and of course we can let it be 3, then you get a mean, which will be location. So most distribution will have location parameter, the scale parameter, and the shape itself. So the shape will give you how it will look like in terms of its histogram. The scale will now be the numbers, whether it is Because if I have a normal distribution and I multiply each value by, let's say, 4, I will only shift the the values, but it won't affect the structure of it. So those are some of the things you look at. And I can shift it by location, by subtracting or adding. It will just move the histogram either to the left or to the right, depending on the value. And so that's how most distributions are. Okay. So now let's see, assuming we did not have the Pareto QQ, how can we now, based on our statistical knowledge in this, be able to say we will now get our own ESPQQ, which can plot both the Pareto and exponential. That will go back to what we did here, last week, which is that we do what? We modify the function. Is that okay? We can do this and then we close. Okay. So I go to ESPP, I run it. Remember that if you want to get it, you just select the function without the parentheses. Run it, everything will display on the screen. Okay. Then what do we do? I need to copy. So I copy this up to the last. Remember, we did functions. When you get a function, the arguments, the next thing is what? Curly bracket. So within that bracket, you have the body of the function. So I copy all of that. Then I come to my here. Then I say modify ESPQQ to produce Pareto QQ output. Okay. So we want this function to be such that it should just, its output should be, so remember the structure of the function name, what comes next? The name, then what comes next? The assignment operator, and then the keyword what? Function. Is that okay? So now it comes, but if we do it this way, it will be, there will be what we call confusion now as to whether to use our own ESP. So the name must be different. So we can say this is my ESP, we call it PAR. So it will do ESP and Pareto QQ together. That's what we want to do. So then I go to the function, I check what's in there. Main is Pareto exponential. So that's why you get the exponential QQ plot over here, because the main is that. But we will delete it. We don't want it to give any name like that. And then we can delete what is over here. Okay. So that's it. Then this check, it checks the data to see whether it is in that particular position. We don't need it. So we can comment it off or take it off. Now, from what we have discussed, what is this? What is X in this case? From what we discussed last week and what I have discussed today, what is X? So that's how you analyze within a function what is going on. If you don't understand, because you have to relate this, which is a code, to your statistics. What are they finding there? They are ordering the data, so it becomes what? In statistics, not rank. If you sort, was it rank? When we wanted ranks, we got the values, the positions. Sort was what? If you sort the data, we just discussed this. In 331, you talk about other statistics. This is what I've been saying all this one. So sort means what? Order. So that's your order statistics. That's why in the plot you see X over there. Look at the Pareto. What did you see? Log X. remember that the Pareto is what? Log of what? X. So look over here. You see you have quantiles of the exponential, quantiles of the exponential. Because the Pareto is related to what? The exponential distribution. Okay, good. So I'll make a comment here. This is what? Order statistics, right? So that's your order statistic. Or empirical quanta. Is everybody okay with this? So that's your empirical quanta. Okay. So you see, we are doing actuarial science, but mainly the tools we are using are statistics. Okay, so similarly, maybe if after this you go and do data science, you can't leave your mathematics, you can't leave your statistics, and of course it will need some computing aspect. But central to all this is statistics. And it's no coincidence that you see that in your actuarial science, you see that in some cases you are doing statistics with our statistics students, and you take some statistics courses. So sometimes some people were not advised properly, and then they moved away to computer science. I mean, but if you want to do anything data, you cannot leave your statistics at all, especially when it comes to modeling and so forth. I mean, yeah. So please take note of that. So that's empirical quanta. Now, what about this? What? How can we explain this? What is it? That is what? That is your sample size. Is that okay? Good, okay. Now, what about this? What about this? Can you? Okay, so let's go in. First, you have negative, right? Log. Then you have this. What can you say about this? If you were to do this, if n is 10, what will happen? If n is 10, please pay attention to this. Whatever we are doing is a theoretical thing I explained. Do you remember I wrote this over here? Where a standard exponential, what do you expect? Lambda is what? 1. So you get what? Negative log, right? So that's what you are seeing there. Then you have 1 minus p. What is p? This is theoretical quanta. So I take the position. It's a theory. So I don't need anything. All I need is the position. So the first data, 1 divided by the sample size, will give me the probability. But because I'm doing this up to the last sample size, I just add 1 to the sample size so that the last one I won't get exactly 1. Because when I get exactly 1, I'll get log 0, which will give me nothing like that. Right. So, whatever we are doing, this is the practical aspect. And if you can't get this, so this is P, it's actually the probability. So if this is 0.5, we have the median. So that's what we've been doing all this. So here, that's it. So that's all you need, I mean, to do this. So if I want to add another one, then X is this. So still that's the empirical quantile. So I can add log this. Then that will give me the Pareto, right? Log dot this. Then I will assign it to log of what? X. So that will be my empirical quantile. Then the rest are just plot. So what do I do? This plot.fun is just plot. So I can take the fun off and also this off. Output, output is return. So you remember return. So I can change this to return. Okay, what else do I have to do? This plot, you need to take, you need to also, it's time, so let me just be quick so that you can go. I need another plot which will be for what? The Pareto, right? So the Pareto, what else do I have to change? The X will be the same, But this will be different, right? The X is this. Wait. Yeah, this one will change to log. Like that. That's all. And then that quantiles of the exponential. Yeah, that's it. Okay. So I'm done with this. Okay, so my function is done. All I did was to introduce a new, this is what? Pareto. Pareto. Pareto case. And this is what? Just the exponential. Exponential case. Okay. So now I'm done. This is okay. So I can now check what was data. Data was, I can go up there and go and copy what we did. Auto claims paid. So I'm now going to generate the same graph, but now two of them will be done at the same time. There. There's a mistake. The S lab for this, the Pareto should be log X. Otherwise, they are all X, and it doesn't. So I need to rerun it for it to take effect. There. Okay, because it's 3, so I can go back again and change this to 2, the power to 2, right? If I do this, let me copy and do it again so that you understand what is going on. So it was 3, but I only need 2, so I just do this, and then I do the plot again. There. Okay. So you see now I have X, standard exponential, and this one. So the first one is exponential, the second one is what? Pareto. So yes, so it means that in doing this I don't need to be calling and we can even add a log normal and add all the others so that you have just one function. As soon as you pass your data through, you get all this at a go. So this is very important, and I must tell you, it's the same thing I'm teaching those who are doing masters. So please take active interest in this. You won't go wrong with it, and learn to perfect yourself. So all the things that you've been doing in natural science, in statistics, in mathematics, most of the concepts you are doing, you can sit down and create your own functions to be doing such stuff. So if there is an existing function, you can take it and modify it. But you can only modify something if you understand what is going on in there. Right? And that's it. If you see plot, we've done plot, so you should know that they said dot plot fun. Because it is some are also linked to C++. Those doing computer science will understand. Okay, so C++ has routines, so R sometimes borrows from there. Okay, so you will see dot plot fun, that is being taken from a package in C++. So when you create your own function, because your namespace does not include that, you won't get it. So you need to bring it to the language that R understands solely in R to use it. Okay, any question? Okay, so let me put this as all the updated one on Sakai. So maybe I can override what I did, right? Should I override it?
Yes, sir.
But please take your time and go through it. Whatever. You can get the ESVP on one side, and then you take what we did. Then you cross-check each of them. What of them. Okay, so I'll send you the assignment. So here, the next one, you are going to generate observation from a normal distribution. How do you generate observation from normal distribution? You use a random, so R norm, right? The sample size is there, the mean, the variance is there, so you can do so. Use the functions in I to plot this data. Repeat this exercise, but in this case, make sure there is no title in your plot. You should be able to modify it to do so. Look for cumulative distribution function for exponential and Pareto distributions. You can go online or in your books and check it. Invert these functions to obtain the quantile function. That's like the exponential one is what I did here. What you need to do is to go and look for the Pareto, in which case the cumulative distribution of the Pareto. Then you invert it yourself to get the quantile function. Write your own functions based on III to obtain these plots. So now you are not going to use the same function, but now you are going to write your own function. I think we wrote one for the exponential, right? Or you can do so. So this function will take in lambda, and it will take in what? A data, because it's out of the data that you will get your P. You need the sample size of the data to get P, like we did over there. So you need the data in that. And then all you do is that 1 over lambda log 1 minus what? The sample size. But 1 to the sample size divided by that. Gives you the. So that's the exercise. Then you can go. I'm done. So I'll send you the video. You do all of it. Let me see. I think it's the same thing. Simulate observation from the exponential distribution. So you do that. Use your function in IB to obtain this plot. Comment on the fit of the. So it's the same thing. So I'll send you this on Sakai as well. Please take your time. Make sure you learn, because your IA will be the same. It will be something like this, as well as your exam. Oh, similar. You see, the words same and similar, are they the same or similar? Or you want the same thing? Of course, I can bring you the same thing, then I'll know those who learn and those who don't learn. Because whatever it is, you need to program. You can do it.